Okay, so this is going to be approaching one of the last derivative rules here, and I wouldn't really say it's something that we're proving. It's more so we're just kind of understanding how to apply this to other equations. Generally it's used on things that are not functions, right? So things that are not vertical line test passing, I guess. So circles, I mean sideways parabolas like this, just loop-de-loops, anything like that. Um, Hyperbolas, stuff like that. Any of that, that's where this is applicable. I mean, it's applicable anywhere. You're using it all the time, but it's just kind of more known, I guess. You're just kind of doing it more discreetly here. So if I'm just going to say I want to take the derivative of x squared plus y squared equals 25. How can I do that? Right? I have y squared here. How am I supposed to take the derivative of y squared? Okay, well, the first thing we're going to do is we're going to take the derivative of each term, right? Because the derivative of a sum is the sum of the derivative. And over here, we're just doing the same thing on each side. We're just taking the derivative of everything, right? So the derivative here, we're going to have 2x plus, and then for y squared, what we're going to have is something involving the chain rule. So we're actually going to view y as a function here. And so we can just say we have like u squared and y is the interior function, right? Because y is a variable, so works here. Basically, we're using the chain rule. We're going to say 2y and then multiplied by dy over dx. And I say that because we're taking the derivative we're taking d over dx. So we're taking the derivative d over dx of y. That's dy over dx. So that's just what it is. Hopefully that makes sense. And then we're just going to be taking that and plugging it right into the equation here. And then I'm going to say this is equal to 0 because the derivative of a constant is 0. Okay, so now we're going to move forward here, and I'm going to say I want to isolate dy over dx because dy over dx is the derivative, and that's what we're solving for. So we're going to say 2y dy dx equals negative 2x, and then because we subtracted 2x from both sides, and then we're going to divide both sides by 2y, so then we have dy over dx equals negative 2x over 2y equals negative x over y. And this is applicable in literally every single, everything based like this. You can use it for all quadrants, so it's not limited. And the reason I make that distinction here is because you could solve this in another way. You could isolate y here. You could say y squared equals 25 minus x squared. I'm just rearranging this original formula right here. Just rearranged it. And then if I solve for y, I'd get y. I'm taking the square root of everything. Square root of 25 minus x squared. Just going to put a line here. Okay. And this gives us the top half of that circle. If we want the bottom half, it'd be y equals negative square root of 25 minus x squared, because obviously square roots can't be negative. So when x exceeds 5, then it becomes an issue. So that's why we put this negative here for the other side here. And so we split it into these two things, and we can't always do that, which is why implicit differentiation is important to be familiarized with, because we can't always split it up like this. Many cases we can, but it's not easy, and it's too tedious, and it's time consuming. Like how we use the chain rule for something like 3x to the 17th, right? We could, or well, that's a bad example. 3x plus 1 to the 17th. We could expand that all we want, but it's just, there's no need to. We can just simply use the chain rule. So it's kind of the same idea. There are going to be ones that you can't expand it, obviously, and there are examples of that in other derivative rules, like, you know, how you gonna expand this? You can't really expand that, take the derivative of it. Anyways, though, that is going to kind of sum up the implicit differentiation. So it's not really too difficult. It may look intimidating the way it's portrayed to you because you're kind of looking at functions that look like this, and it might be confusing. Um, but just know, really, all you're doing is you're just taking the derivative of everything inside it. So every term, you're saying the sum rule, you're applying it. Sometimes you'll be using the product rule. Really, the main takeaway here is when you're dealing with y, just know the derivative of y is dy over dx, right? We're not really gonna get a solid answer there because y is its own thing and it's just not something we can work with like that. Okay, because we don't know the function that y is. We do not know what y is, so we're just going to denote it as dy over dx. And, if I were to say like 3x, 3x, or not 3x, 3y squared, and I would take the derivative of that, I'm going to be employing the constant multiple rule. I'm going to be saying, okay, y squared, we're going to be using the chain rule here. It's going to be 2y, and then I'm going to multiply that by dy over dx, and then I can, just say 6y dy dx, right? So it's really not too complicated. Again, it does look kind of intimidating when you see it the first time, but trust me, it's not a big deal. Just kind of practice with it, solve a couple equations, use it, and it'll become pretty easy. It's not like we're introducing really anything new here, other than what I just showed you, that dy over dx part. But that's really it. So that's just going to do it for implicit differentiation.